Welcome to lecture number 3 of Chem 152, or General Chemistry 2. Again, remembering this is actually the second content lecture because lecture 1 was just syllabus and course policies. This lecture is on the properties of liquids and phase transitions, and it covers OpenStax sections 10.2 through 10.3. So just reiterating what we learned last time about intermolecular forces, remembering that inter means between, so intermolecular forces are those between molecules. These are weak forces between separate individual atoms or molecules, and the three main types we learned about were hydrogen bonding, dipole-dipole interactions, and dispersion forces. So to summarize these forces and their effects on physical properties. So the blue arrow going up here means stronger IMFs, or stronger intermolecular forces. So as intermolecular force strength increases, the state of matter or the phase is going to change. So typically from a gas to a liquid to a solid as force strength increases. Melting point and boiling point will increase along with the heat of vaporization, which is the phase transition from a liquid to a gas or a vapor, and the heat of fusion, which is the phase transition from a solid to a liquid, as well as the heat of sublimation. And sublimation is the direct conversion from a solid to a gas, which is actually just the sum of these two heats. The solubility of water, viscosity, and surface tension will all also increase as intermolecular force strength increases. There are two that will decrease as IMF strength increases. These two are vapor pressure and volatility, and these two kind of go hand in hand with one another. And we'll learn more about these physical properties in this lecture. So all of these are directly related to how much energy is needed to overcome the intermolecular forces that are holding the molecules together. All right, now, as mentioned, IMFs will generally determine what phase a substance will be in at a given temperature. So this is a similar version of the figure we saw at the start of last lecture, where as kinetic energy increases, or basically as temperature increases, this is a force that will pull molecules apart. So this can result in a phase transition from a solid to a liquid to a gas, whereas intermolecular forces attempt to hold molecules together. And so if you were to decrease kinetic energy, IMF force strength would win out, and we would see a substance move into the condense phase. So this is summarized in these bullet points. As temperature increases, the kinetic energy or particle motion increases, which means you need stronger IMFs to hold particles together in place. So solids, if something exists in the solid phase, this typically means you have low kinetic energy, low temperature, and or strong IMFs, or the IMFs are at least strong enough to keep these particles in contact with each other and in fixed positions. In a liquid, we generally have low kinetic energy or low temperatures, and or we have IMFs that are strong enough to keep the particles in contact with one another, but not so strong that they can be kept in fixed positions. And finally, with gases, IMFs are not strong enough to withstand the kinetic energy. Particles are not held in contact with each other, and they move around randomly to fill both the shape and the volume of the container that they are in. All right, so summarizing some phase changes. So you should be familiar with all 6 of these phase changes. So between a solid and a liquid, obviously going from a liquid to a solid is freezing, and from a solid to a liquid is melting. Then between a liquid and a gas, we have vaporization, which can also be called boiling or evaporation. And from a gas to a liquid, we have condensation. So everyone is going to remember these 4 since they're most applicable to our everyday lives. The last 2 can be a little trickier to remember. So solid to a gas, this is sublimation, and then a gas to a solid is deposition. I usually try to remember this one. I remember deposition. So if something is going from a solid to a gas, it's depositing. It's forming a solid. It's depositing on a surface. And then I can usually remember that the other one is sublimation. Solid to gas, sublimation. This is also the phase transition most commonly seen in everyday life with dry ice. Dry ice is a solid carbon dioxide that sublimates into a gas at standard temperature and pressure conditions. All right, so these phase changes are also summarized here on this slide. I'm going to keep it moving. So a phase change occurs when enough energy, which is typically in the form of heat, is either added or removed to cause the substance to move from one phase to another. There are 6 phase changes, which we just outlined previously: the liquid to vapor phase transitions, vaporization and condensation, solid to liquid, so melting and freezing, and solid to vapor, sublimation, deposition. So starting with the liquid to vapor phase changes, this can be described as vaporization, going from a liquid to a gas or vapor. The reverse is condensation. So the amount of energy needed to convert a mole of a liquid to a vapor is the molar enthalpy of vaporization. You should remember this term from General Chemistry 1, delta H. This stands for the molar enthalpy, or the change in enthalpy. So delta H, VAP, again, is molar enthalpy of vaporization, the amount of energy, typically in the form of heat, needed to convert a mole of a substance from a liquid to a vapor, or the reverse. It's the same magnitude. It would just be, adding heat versus removing heat. Now, liquefaction can be achieved by increasing pressure as well as decreasing temperature. The increased pressure brings molecules closer together, allowing the attractive forces of the IMF to come into play. The math problems we're going to look at are going to just be looking at temperature changes by adding or removing heat, but it is important to note that you can liquefy something from a gas by simply compressing it, by increasing the pressure. Next, evaporation and vapor pressure. So the vapor pressure of a liquid is the gas pressure due to its vapor when a dynamic equilibrium exists between evaporation and condensation at a certain temperature. We're going to see this term here used a lot in this course, a dynamic equilibrium. So that's what the double arrows indicate here. So basically, this is when the rate of the forward and the reverse reaction are equal to one another. So let's pretend we took some water, we put it inside an Erlenmeyer flask, and we sealed that Erlenmeyer flask with a little cap. Now, evaporation is going to occur when water exists as a liquid. It is always evaporating. It doesn't matter what the temperature is. Now, the more you increase the temperature, the more the rate of evaporation will increase, but evaporation is always occurring if you have liquid water. So evaporation begins, so a few of these water molecules are able to escape from the liquid phase into the gas phase. Now, evaporation continues, but as you get more and more water molecules up here in the vapor phase, condensation will begin to occur. So you get the reverse situation occurring, where some of this vapor condenses back into a liquid. And eventually you will reach a point where you have a dynamic equilibrium. So again, a dynamic equilibrium refers to the point at which the rate of evaporation equals the rate of condensation. So the rates of these reactions are equal to one another. That does not mean that you have equal amounts of liquid and vapor. It simply means the rates of these reactions are equal. So this is where vapor pressure comes from. Vapor pressure is the partial gas pressure due to the gas molecules present above the surface of the liquid. This is what a vapor pressure is. It's the gas molecules that exist above the surface of a liquid, the gas molecules that have evaporated away. Now, vapor pressure, intermolecular forces, and temperature. How are these three things related to one another? Stronger intermolecular forces actually result in a lower vapor pressure. So vapor pressure along with volatility were the two categories or the two physical properties that have an inverse relationship to intermolecular force strength. So if we think about it this way, right, if molecules cannot easily break away from the liquid, so if you have really strong IMFs, the molecules can't easily break away from the rest of those liquid molecules. They therefore can't enter the gas phase. If they can't enter the gas phase or the vapor phase, the number of gas molecules above the liquid will be lower, and therefore the vapor pressure will be lower. So again, we have an inverse relationship between IMF force strength and vapor pressure. As IMF strength increases, vapor pressure decreases, and vice versa. Vapor pressure is measured at a certain temperature. At higher temperatures, the vapor pressure will actually increase. And so this makes sense, right? If we increase the temperature, there's more kinetic energy. If there's more kinetic energy, there are going to be more molecules that have enough energy to overcome the IMFs that are holding them in that liquid phase. All right, so here we see a chart of 4 liquids: ethyl ether, ethyl alcohol, water, and ethylene glycol. So consider the 4 liquids shown in the graph above. Look up the chemical structure for each and identify what IMFs are present. Which liquid has the highest vapor pressure at a temperature of 35 degrees Celsius and why? So I would ask you at this moment to pause the video and look up the chemical or the molecular structure for each of these 4 molecules, or at least you know the structure for water, but look up the structure for ethyl ether, ethyl alcohol, and ethylene glycol. Once you've done this, analyze the chart. So we've got temperature on the x-axis increasing from left to right, and we've got vapor pressure on the y-axis increasing from bottom to top. First, determine which liquid has the highest vapor pressure at a temperature of 35 degrees Celsius, and then when you look at those structures, ask yourselves why. Okay, so hopefully you paused the video there and tried to answer this problem. First question, which liquid has the highest vapor pressure at a temperature of 35 degrees Celsius? If we analyze the graph, so conveniently we've got a little dashed line here placed at 35 degrees Celsius, we can see that ethylene glycol is not even registering a vapor pressure at 35 degrees Celsius. We don't start seeing a vapor pressure until just past 80. So if we draw our dashed line, water has a vapor pressure probably in the single digits. Ethyl alcohol is probably somewhere around maybe 15 to 20 kilopascals. It's a little hard to tell from these units. And the ethyl ether is all the way up here. It looks to be somewhere around 100 kilopascals. So the answer here, definitely ethyl ether. It has the highest vapor pressure at 35 degrees Celsius. The second question then is why? If you look up the structure of these molecules, you will find ethyl alcohol, it's CH3CH2 with an OH. Water is H2O. Ethylene glycol is 2 CH2s with OHs on either side, whereas ethyl ether is an oxygen in the center with 2 CH2CH3 groups on either side. Now, the point being is when you look up these structures, you should find that the ethylene glycol, the water, and the ethyl alcohol all have OH groups. They all have hydrogens directly bonded to oxygens, which means they all exhibit hydrogen bonding, whereas the ethyl ether, it is polar, but it does not exhibit hydrogen bonding, so it would experience or exhibit dipole-dipole interactions only. So ethyl ether has the weakest intermolecular forces of the 4, and so therefore it will have the higher vapor pressure at the same temperature. All right, I've got another practice problem for you to try. So again, please pause the video and give these questions a try. Which compound in each of the following pair has the higher vapor pressure at the same temperature? All right. Here are the correct answers. So for the first 4, it's the first answer, and for the last one, it's the second answer. How do I determine these answers? Well, first, what are we being asked? We're being asked to find which compound has the higher vapor pressure. So if we're looking for the higher vapor pressure, we are therefore looking for the molecule that has the weaker intermolecular forces. So starting with CO2 versus CS2, if you draw these two molecules out, you'll find they have basically the exact same Lewis structures. Carbon in the center, double bonded to oxygen or sulfur atoms on the outside. So these things have the same Lewis structure. They both have the same linear geometry, and so they are both actually non-polar. Both of these molecules are non-polar. They both would exhibit dispersion forces only. So then we need to ask, Okay, dispersion forces only for both. Which one has the stronger dispersion forces? And so if you're breaking a tie, remember the easiest way to break the tie with dispersion forces is molar mass. Whichever one is bigger, has the bigger molar mass, and is therefore more polarizable, will have the stronger dispersion forces. And CS2 has the bigger molar mass. It has the stronger dispersion forces, which means therefore that CO2 has the higher vapor pressure. A similar answer or similar reasoning to the second question. Both of these have CH carbons and hydrogens only, so they're both nonpolar. So the smaller molecule, the one with the smaller molar mass, is going to have the weaker dispersion forces and then the higher vapor pressure. The third one, these are two different pentane isomers. So we looked at this in the lecture 2 on intermolecular forces. This is the formula for neopentane. This is the formula for N-pentane. So they have the same molar mass. They're both nonpolar, both dispersion forces only. They have the same molar same molar mass. So they are both C5H12. So you want to look for the one that's more branched. The one that's more branched and has that more spherical shape is going to have less surface area, weaker dispersion forces, and therefore the higher vapor pressure. Number 4, now we've got some differences going on here. This first molecule is non-polar, dispersion forces only. This second molecule is going to be polar. If you draw out its Lewis structure, you'll find that we've got a bent geometry. This molecule is polar. So this molecule would have dipole-dipole interactions. It has the stronger forces, which means this is our answer. It has dispersion only, weaker intermolecular forces, higher vapor pressure. And last one, this molecule, as we just mentioned, has dipole-dipole interactions. This molecule right here is going to have hydrogen bonding, which is the strongest IMF. And so now it flips, and this molecule is the answer. It's got the weaker forces and therefore the higher vapor pressure. All right, next we're going to look at the relationship between vapor pressure and boiling point. So the temperature at which a liquid's vapor pressure equals the atmospheric pressure is the liquid's boiling point. So let me repeat that. The temperature at which a liquid's vapor pressure equals the atmospheric pressure is the liquid's boiling point. Basically, it's when you have the same number of molecules escaping as you have surrounding that liquid from the atmospheric pressure. This is why the why the boiling point of liquids will change drastically as the pressure changes. So especially as you go like up into elevation. So for example, water has a much lower boiling point at elevation. So like Mount Everest, water has a boiling point, I believe it's somewhere around 68 to 70 degrees Celsius. Much lower than the standard boiling point because when you're up on Mount Everest, the elevation is much higher, the atmospheric pressure is much lower. So there's less pressure pushing down on the liquid and it escapes into the vapor phase more easily. Now, the normal boiling point, you should remember this term from Chem 1. The normal boiling point is the boiling point of a liquid at an atmospheric pressure of 1 atmosphere, which is 101.3 kilopascals. So that's that horizontal line on the graph right here. This is the normal boiling point line. So what we can do then is we can track the normal boiling points at least for 3 of these liquids. We see for ethyl ether, its boiling point is at 35 degrees Celsius. This is the point at which its vapor pressure crosses with that normal boiling point line. For ethyl alcohol, this looks to be somewhere around, roughly around 80 degrees Celsius, maybe 78, 79 degrees Celsius. And then for water, it's at 100 degrees Celsius. And I kind of just answered this question for you. Okay, so just summarizing one more time, vapor pressure of a liquid is the gas pressure due to its vapor when a dynamic equilibrium exists between condensation and evaporation at a certain temperature. So as temperature increases, this means kinetic energy is increasing, meaning the percent of molecules in the gas phase are increasing, and therefore vapor pressure increases. All right, so let's look now at the mathematical relationship between these things. So you'll notice When we look at this graph of vapor pressure versus temperature, the relationship between the two is non-linear, right? See how it looks almost exponential, right? As it begins increasing, the speed of that increase, well, increases. It begins to increase more rapidly. This suggests an exponential relationship between temperature and vapor pressure. And so this is exponential, and it's described by this formula where P for vapor pressure equals A times E. So this is lowercase e, this is the constant E, it's Euler's number, raised to the negative delta H vaporization over RT power. Now this version is a little complicated. It can be useful if you're explicitly being asked to solve for P or A, but we're going to linearize it. We're going to take the natural log of both sides, and we're going to get rid of that E. So taking the natural log of both sides, it rearranges to this linear equation. We get the natural log of P equals delta H vaporization over RT. The ln E disappeared, which is why you don't see E in this version, plus natural log of A. So again, P is the vapor pressure. This pressure is typically going to be in kilopascals, but it could be in atmospheres as well. T is temperature. Temperature is going to be in Kelvin. R is the ideal gas constant, which here is 8.314 joule per mole Kelvin. A is simply a constant specific to that substance, and then delta H vaporization, we mentioned already, is the molar enthalpy of vaporization. So let's look at the relationship between these things. The equation can be written as shown, where we call natural log of P Ry. We call the delta H vaporization over R the M. We'll call 1 over T X, and then the natural log A becomes B, becomes the Y-intercept here. So oftentimes, one method of determining the enthalpy of vaporization for a substance is to measure its vapor pressure at different temperatures. Then, if you plot a graph of ln P versus 1 over T, so the inverse of temperature on the x-axis, the natural log of the pressure on the y-axis, the slope of that line gives you delta H vaporization over R, so you can determine the molar enthalpy of vaporization. So you should be aware of this version of the equation. You will use it on some problems, especially if you're given a problem where you've got a graph of ln of P versus 1 of T. Now the version we're going to use more commonly is the one that's derived like so. So first we're going to start by using the equation for slope. So harkening back to our algebra days, we know that slope m equals y2 minus y1 over x2 minus x1. So using the variables I established above, I'm going to say m equals negative delta h vape over r equals y2 minus y1. So here's my y value, so ln p2 minus ln p1 over x2 minus x1, and x here is 1 over t, so 1 over t2 minus 1 over t1. We're going to rearrange this. So what I did here is I took this and I multiplied it from the right to the left, and that leaves natural log of p2 over p1. I recombine these into one natural log equals negative delta H vaporization over R, parentheses 1 over T2 minus 1 over T1. So you will often see a version of the equation that looks like this. The version I'm going to use is this one right here. This is called the Clausius-Clapeyron equation. So this is almost identical to the version I showed you on the previous slide. All I did was I took that negative that was right here and I distributed it to the terms on the inside, and so that's why the orders of the temperatures flipped. So you can see this version versus this version just has the orders of these temperature terms flipped and no negative sign here. This is called the Clausius-Clapeyron equation, and it can be used to calculate the enthalpy of vaporization if we know the vapor pressure of a substance at two different temperatures. So again, P is vapor pressure, T is temperature in Kelvin, delta H vaporization is that molar enthalpy of vaporization, and R is the ideal gas constant, which is here is 8.314 joule per K mole. A couple notes, just again, noting that some sources have these switched and a negative sign in front, so make sure you double check if you're using a different source. Please pay attention to your units. Temperature values gotta be in K. The gas constant R needs to be in joule per K mole. As far as pressure goes, the pressure units just need to match so they can cancel. You can use different pressure units. You could use kilopascal, atmosphere, whatever, as long as both pressure values are in the same unit. All right, so let's show you the first type of problem you may get. Suppose you are given a graph that looks like this and told the vapor pressure of ethanol was measured at various temperatures, and the graph of ln P versus 1 over T was plotted in order to determine the enthalpy of vaporization. The linear regression equation is displayed on the chart, and it gives the slope of the line. So remember, this is the type of problem where we've got natural log of vapor pressure versus 1 over T graphed on the x-axis. So this is when you use that first version, that version I showed where I had the variables beneath it. So to be more specific, this version right here, you're going to use this version of the equation for a problem like this. So what that version of the equation told us is that the slope of this line equals negative delta H vaporization over R. So on a problem like this, all you need to do is set negative delta H vaporization over R equal to the slope of the line. The units on that slope are actually just going to be Kelvin. So we have negative 4,886.9 Kelvin equals negative delta H vaporization over 8.314 joule per mole Kelvin. So I simply multiply this term from the right to the left. The units of Kelvin cancel, and this gives me an answer of 40,629 joule per mole. These values are more commonly put in kilojoules because they're very large. So I would say final answer here would be 40,000 or 40.629 kilojoules per mole. So be on the lookout for a problem like this where you'll be given a graph, and make sure you use the first version of the equation, that basically the linearized version of the equation, not the version that has the T1, T2, P1, P2 in it. All right, let's look at a second type of example problem. Suppose you are told that a certain liquid has a vapor pressure of 88 torr at 45 degrees Celsius and 39 torr at 25 degrees Celsius. What is its enthalpy of vaporization? All right, so what you're going to want to do here is you're going to use that version of the Clausius-Clapeyron equation with the numbers in it, right? If I look at the context of this problem, see how you're given two pressure values and two temperature values. If you're given two different temperature and or pressure values, you need to use this version. You need to use the Clausius-Clapeyron equation. So we're given P1, P2, T1, and T2. R is a constant, so we need to solve for delta H vaporization. So I'm going to take this equation, rearrange it, and solve for delta H vaporization. So I don't have the work written out for this problem type. What you would do here, I would encourage you to pause the video and give this one a try on your own. Use this version of the equation. So you're solving for delta H vaporization. You can plug in the gas constant R right here. Plug in your pressure values for P1 and P2, and plug in your temperature values for T1 and T2. Just be careful of a couple things. First, make sure your pressure and temperature values match. So personally, I would call this P1, which would make this T1. So I'd plug in 88 torr right here, and I would take that 45 degrees Celsius, convert it to Kelvin, and plug it in for T1 right there. Then 39 torr would be my P2, plugged in right there, and 25 degrees Celsius would be my T2. Just convert it to Kelvin and plug it in right there. So go ahead and pause the video and see if you can solve for the correct answer here. All right, correct answer on this one, you should have gotten something near 32.1 kilojoules per mole. Oh, there we go. Slide was frozen. All right. Example problem type number 3. Suppose you are told the enthalpy of vaporization of isopropanol is 44.0 kilojoules per mole. So now you're given the enthalpy of vaporization. You are told that at 39.5 degrees Celsius, its vapor pressure is 100 milligrams mercury, and this is a unit of pressure. What is its vapor pressure at 67.8 degrees Celsius? All right, so we again want to start with the Clausius-Clapeyron equation. Now, again, make sure your units are compatible, notice that the enthalpy of vaporization is in units of kilojoules per mole. When you go to plug this in, you need to convert it to joules because the ideal gas constant R has units of joules. So make sure you convert this to joules before you plug it in. All right, now a vapor pressure is going to be our unknown. If a vapor pressure is going to be on your unknown, I do have a small tip for you here. It makes your life a little bit easier to let P2 be the unknown. So what I'm going to do is I'm going to take this natural log, I'm going to split it back into its original pieces. So ln P2 minus ln P1 equals delta H vaporization over R multiplied by 1 over T1 minus 1 over T2. Then I simply need to move the ln of P1 term from the left to the right side of the equation. So here we have our equation set up and ready to go. Now all you need to do, convert this to joules per mole, plug it in here, plug the ideal gas constant in for R, plug this in as your T1, just convert it to Kelvin, plug this in as your P1, plug this in as your T2, again just convert to Kelvin, solve for everything on the right side. Then you'll just have one more step to do. Once you've got all of this solved, it's going to be natural log P2 equals some number. You need to get that unknown out of the natural log, and you do this by raising both sides to basically e to the power on both sides. So if you have natural log P2 equals 20, for example, you would raise, or you'd put e to the power on both sides. So you would do e to the natural log P2 equals e to the 20. And so that e natural log cancel out, just leaving P2 equals e to the 20 in this hypothetical example. Again, I don't have the work shown for this one. I just wanted to show the derivation. I would like you to give this one a try on your own and see if you can find the right answer. Okay, correct answer here should be somewhere around 408 millimeters mercury. All right, and one more problem type you may see. This one states, for benzene, the normal boiling point is 80.1 degrees Celsius, and the enthalpy of vaporization is 30.8 kilojoules per mole. What is the boiling point of benzene in Denver, where the atmospheric pressure is 83.4 kilopascals? All right, so now we have a boiling point is our unknown. A boiling point is the unknown. All right, so once again, I just want to point out, make sure you're using compatible units. Make sure that delta H value is converted to joules per mole before you plug it in. Recall, a big hint here is to recall the definition of a boiling point. So see how it says the normal boiling point. So you're given T2, but you're not directly given P2. You're kind of implicitly given it through that term normal, though. Remember, normal boiling point is the boiling point at atmospheric pressure, which is 1 atmosphere or 101.3 kilopascals. So my P2 value then is going to be 101.3 kilopascals. My other hint for you here is that I do recommend making T1 the unknown. Making T1 the unknown is a little bit easier. It's slightly easier than having to solve for T2. So what I'm going to do is I took this term right here and I divided it from the right to the left, which gives me ln P2 over P1 divided by delta H vaporization over R equals my term on the right. Then what I did is I basically just flipped that R up to the top, right? It's in the denominator of the denominator, so it can be flipped up to the numerator. And then finally, this 1 over T2 term is just moved via addition from the right to the left side. And so I get this equation right here. 1 over T1 equals this big mess plus 1 over T2. So to solve this one, you go ahead and plug in 101.3 kilopascals for P2. You can plug in 83.4 kilopascals for P1. 30.8 kilojoules per mole, convert that to joules per mole, plug it in for delta H vaporization, plug in your ideal gas constant for R, and plug in 80.1 degrees Celsius for T2. Again, just make sure you convert it to Kelvin, and work your way through this problem and solve for T1. So please try this algebra on your own and see if you can come up with the correct answer. All right, and the correct answer here, you should have gotten around 346.9 Kelvin or 73.8 degrees Celsius. Okay, that's the end of the first half of this lecture. I've got one more Clausius-Clapeyron equation problem for you to try. So I encourage you to, again, pause the video, give this one a try. It's similar to the questions, one of the questions on the previous couple slides. Okay, if you gave this one a try, the correct answer is 156 millimeters mercury. All right, so this lecture is being split into two halves since it's a little longer. This is the end of the first half. I'll see you in the next video for the second part.